Adaptive Computation LLC, a spin-off company from Caltech, sparse sensor and in-memory processing deep neural network processor, and machine intelligence software application. Team capability: Dr. Duong as CEO and CTO, PhD UCI in Neural Control and Systems. Dr. Nam Trang as VP of Data Science, PhD in UC Berkeley in Mathematics. For contributions, significant contributions of his works include 1. Effective mapping from EVIB to solve real-time moving object recognition based on a single database, real-time learning and operation, and real-time adaptation. 2. Self-dynamic and supervised learning to facilitate a brain-like learning manner for long-term memory. 3. Sparse image with 60-time intensity pixel reduction for the DARPA IP2 program. 4. Let in-memory processing neural network hardware wrote for the first time a radiation adaptation algorithm to adapt the electronic effects under ration environments for JPL/NASA, and flew the first space neural network hardware online learning system, STRVB, in 1994. Achievements: for his invention of on-chip processing to improve the cost of NASA missions, he received the 2002 Exceptional NASA Space Act Award for the creative development of exceptional scientific and technical contributions for Aerospace Technology Program of NASA, and 2004, 2006, and 2009, the Standard NASA Space Act Award, and 30 NASA Technical Innovation and Monetary Awards. 12 patents and monetary awards, Caltech and NASA as assignees, 4 patents, adaptive computation, 2 pending patents, and 5 provisional patents. He has published 115 papers and new technology reports and 3 chapters of books. The problem and state of the art. SWaP-C systems for object detection, recognition, and tracking are facing several problems, including Moor's law reaches to the limit while new semiconductor materials and computing direction like spin electrons are long-term goals. B. Higher resolution color image demands for small object detection. C. Nvidia architecture based von Neumann digital base architecture requires data transfer for power-hungry digital computation requests. Those pose challenges to obtain low SWaP-C systems. There are several technical blocks that need to be optimized: sensory data, system architecture, and computing algorithms. Sparse imagers to remove redundant and irrelevant data to get effective saliency information. 2. In-memory processing architecture where analog sensor data works directly at weight vector memory location. And 3. Dynamic algorithm where memory data is adaptable and optimized. ADC possesses sparse data with 60 times intensity pixel reduction of color data, while maintaining the equivalent performance in deep neural network and intelligent search engines developed by ADC. Hybrid in-memory computing architecture for high speeds and low power approach, where the PI developed at JPL. State of the art. Deep learning, a statistical, data-driven approach, requires huge upfront databases, and it also requires more powered computation machine and a lot more time to train. State of the art, as NVIDIA architecture which facilitates color data, more data, von Neumann base architecture to require time and power consumption, and deep learning base architecture, examples are YOLO or ResNet base architecture, over one parameter space, which is far reach for SWaP-C constraints. Advancing the state of the art. ADC is equipped with sparse sensor approach, where grayscale pixels are collected and computed at the pixel level via local pixel neighborhoods, 8x8, to reduce intensity by 60 times. For example, based on a 22 nanometer CMOS technology, sparse images extracted in pixel local computation requires 101 milliwatts, or 60 megapixels. In addition, it enables cybersecurity to encode raw data from the hackers. Hybrid in-memory processing architecture, analog current as sparse pixel, and 8-bit MDAC as digital weight value, developed at JPL and Dr. Duong, was leading this effort. The sparse analog pixel array uses fully parallel readout to multiple hybrid 8-bit MDAC arrays, asynchronously as improving speed and reducing power consumption. The active and adjustable ADC architecture, which uses adaptable unsupervised and dynamic supervised learning, avoids statistical and blanket techniques, like deep neural networks, to optimize memory data and computations. The potential barrier of the hybrid approach is processing variation, where the weight values no longer hold up its precision, to challenge the inaccuracy of computation. ADC introduces the compensation technique in design with an upper bound tolerant variation of 10% to calibrate its variation. In addition, the test phase can be required with less than 8-bit precision. For this demonstration, all computation will be done on this Raspberry Pi, and we will use a full color video of a drone. We will select the object we want to track in the first frame. For this demo, we will do it manually, but for autonomous systems, we can combine a supervised learning architecture for this initial target acquisition and then let our architecture handle the tracking. This initial image we have selected will be the only information provided to our architecture, no large databases. Now we will run the full color image video and begin tracking. Here you will see two videos. The video on the left is the original footage provided of the drone. The video on the right is the real-time conversion from full color image into 61 times intensity reduction sparse image, as well as tracking. By extracting features from the previous frame, we're able to adapt and learn the object to detect it in the current frame. This adaptation allows the architecture to conquer the initial blurry images, changes in object orientation, changes in resolution, and sudden camera zooms. For the computational power of a Raspberry Pi, this enables us to achieve our SWaP-C goals. Finally, for defense and commercial use, for the past 3 years, we've seen small drones revolutionize the battlefield. However, current platforms are susceptible to jamming or are guided with fiber optic cables, which limits range. With BISIS, we can overcome these limitations by enabling drones to autonomously maintain tracking of their target. BISIS also has application in hypersonic interceptors due to fast tracking speeds and the ability to do internal computing. For larger platforms such as missiles, that allows for more space and weight for computation and internal computing and tracking, which prevents electronic countermeasures. Furthermore, BISIS is able to cope with rapid changes in resolution and changes in object orientation and size suited for the high speeds these weapons travel at. For commercial use, this means it can be used for self-driving cars or security.